day to everyone. I am Nicolas and I am a PhD student coming from Politecnico di Torino. This presentation aims to show you part of my research project and it is titled Engineering Properties of High Wrap Asphalt Mixtures Containing Recycled Waste Plastics. The presentation is organized in four main parts. After introducing the sustainable asphalt mixture topic, I will describe the objectives and experimental program of my research and finally results and conclusion. Nowadays, scientific community and asphalt industry are developing sustainable technologies to maximize the use of recycled material such as wrap and waste plastics in asphalt mixtures. Despite the restriction limiting the wrap content to 25–30% in new hot asphalt mixtures, the trend is to increase the wrap even further. However, the wrap needs to be appropriately treated with rejuvenating agents because the material is made up with aggregates and very aged bitumen. On the other hand, what happens to our plastics after their first use? By looking at the graph on the left, we can see that just 9% of this material is recycled, 22% is dumped illegally on the environment, while 50% is sent to regulated landfills and 19% is incinerated. As civil engineer, we can focus just on the last two pieces of this diagram, and we aim to find an alternative life to this material. Plastics can be incorporated in asphalt mixtures through three different technologies. In the wet method, low melting plastics are added and mixed directly to the bitumen until an homogeneous binder phase is achieved. In the hybrid and dry method, high melting and low melting plastics are added to the mixtures, modifying not the binder phase but the entire mixture. This is the process to produce and use PMB in asphalt mixtures. However, increasing the wrap content leads to less virgin PMB in our asphalt mixtures, and so less polymer modification of the mixture. For such a reason, PMA technique tries to overcome this problem because the polymer is directly added to the asphalt mixture. For all the reasons discussed before, this project wants to find an optimal formulation that synergistically incorporates all this material without compromising performance and durability of asphalt mixtures, develop an appropriate mixing procedure, miming in the lab what occurs in real asphalt plants, and compare engineering properties in terms of workability, volumetric and mechanical characteristics between PMB and PMA mixtures. The asphalt mixtures investigated in the study were produced by combining different base materials. Two sets of asphalt mixtures modified with waste plastics were prepared using two different levels of polymeric compound, 0.3% ACR-SP1 and 0.5% ACR-SP2 by weight of the back mixtures. Additionally, a set of control mixtures with PMB instead of neat binder and polymeric compound was investigated to compare the effect of polymer modification via the hybrid method with those of standard modification via the wet method. Finally, another control mixture containing 0.3% of polymeric compound and only virgin aggregate AC-SP1 was tested to isolate the influence of wrap. A key aspect in the study was to find an appropriate laboratory mixing procedure miming the step occurring in real asphalt plants. Virgin aggregate was heated to 280 degrees centigrade, meanwhile wrap was sprayed to 70 degrees and the rejuvenator was sprayed on it, leaving it sufficient time to penetrate inside the wrap, restoring chemical and physical structures of aged bitumen. The contact between these materials produced a thermal shock, allowing both to reach the desired mixing temperature set equal to 170. The polymeric compound was then introduced and mixed with virgin aggregate and wrap for further 2 minutes before the addition of filler and asphalt binder. When mixing was completed, the asphalt was held in a mixer for several minutes to simulate the transport phase at the paving site. Finally, the blend was further mixed to simulate the action of a paver. In this study, workability properties were assessed by using Construction Densification Index (CDI). The CDI is calculated as the area under the compaction curve of giratory specimens from the 8th rotation up to the one corresponding to 92% of compaction. Specifically, the lower the CDI, the better the workability of the mixture. The addition of 0.3% plastics via the hybrid technique resulted in better workability during the compaction phase, especially at higher total binder content. However, increasing the polymer content required more virgin bitumen to achieve the desired level of compaction. This outcome is due to an increased stiffening effect caused by the higher amount of plastic granules present inside the blend. The volumetric characterization of asphalt mixtures included evaluation of air voids at 10, 120 and 200 gyrations. The graph illustrated the variation of voids as a function of the total binder content of the different mixtures. Air voids values decreased with increasing total binder content, with the curves corresponding to ACR-SP1 and ACR-PMB showing similar trend. By increasing the plastic content to 0.5% plastic resulted in a significantly different response. As a result, more virgin binding is required to achieve predefined degrees of compaction. Mechanical properties were assessed by means of indirect tensile modulus and indirect tensile strength tests. Stiffness moduli were evaluated at 10, 20 and 40 degrees, showing decreasing value with increasing binder dosage for all mixtures. In addition, ACR-SP2 exhibited the highest stiffness, followed by ACR-SP1 and ACR-PMB. The differences were more pronounced at 40 degrees. This result can be attributed to the highest polymer content present in hybrid blends compared to the wet blends. Regression analysis was carried out and the power law model appeared to be the most appropriate model for interpolating the data obtained. Finally, seems that all the regression curves converge to the mixtures without wrap. Regression curves in previous slide were used to predict stiffness moduli at a fixed total binder content set equal to 4%. ACR-SP2 is confirmed as the most rigid mixture. In any case, wrap addition leads to higher stiffness as expected. Finally, I want to emphasize the differences between ACR-SP1 and AC-SP1. These two mixtures have the same composition except for the use of solely virgin aggregate in the ladder. The difference in the two mixtures is around 85% as it is due only to the wrap. Strength properties were evaluated by means of indirect tensile strength tests. Mixture AC-SP1 exhibited significantly lower strength values compared to the other mixtures, confirming the prominent role of wrap on mechanical properties of the material. By looking at the mixture containing wrap, blends produced using hybrid technology showed greater strength than those produced using wet technologies. Moreover, increasing the polymeric compound content from 0.3% to 0.5% resulted in a significantly increase in ITS of hybrid mixtures. Finally, it can be concluded that recycled waste plastics have good potential for their use in hot mixed asphalt with high content of wrap. In particular, a laboratory mixing procedure has been developed to produce asphalt mixtures containing high wrap dosage and recycled waste plastics. The addition of 0.3% of plastics gave slightly better workability properties than the controlled PMB mixtures. The excessive use of recycled plastics reduced workability and the degree of compaction potentially negatively impact the field performances. Finally, despite the predominant role of wrap in mechanical properties of the mixture, the addition of plastics increased stiffness and strength values compared to ACR-PMB. Further research is needed to investigate other mechanical properties in terms of fatigue and rotting resistance. Thank you for your attention.